Okay, let's discuss aspects related to the safe operation and installation of industrial manipulators. In matters of robot safety, one should consider that the safety of humans comes first, then the safety of the robot, then the safety of other related equipment. In order to comply to requirements related to the installation or operation of industrial robots, there are three main ISO standards that one should consider. Those are ISO 10218-1 as well as -2 and ISO Technical Specification 15066. ISO 10218-1 mainly contains information that is important for the designers of industrial manipulators because it considers aspects such as singularity protection, component malfunctioning, as well as motion control. Secondarily, it also contains information for robot users. That is, it defines the reduced speed control, meaning that the velocity at the tool center point should not exceed 250 millimeters per second, which is also called the reduced safety speed. It defines operational modes. That is, there are three operational modes: manual reduced speed mode, which is the mode in which the robot can be jogged using the teach pendant at a velocity lower than 250 millimeters per second. Then there is the manual high speed mode at which the robot can be jogged using the teach pendant using a velocity higher than 250 millimeters per second. And there is the automatic mode in which there are no velocity limitations on the industrial manipulator and it cannot be operated from the teach pendant, but it will follow the instructions set in its task program. ISO 10218-2 might be something that you more commonly encounter, as it deals with aspects such as the commissioning of the robot, its maintenance, repair, safety distances that must be kept in between a worker and a robot, as well as hazard identification. When it comes to hazard identification, I would like you to please take a look at figure 21. It shows a flowchart for robot installation and integration. And in the first stage, one should conduct a component and process failure modes and effects analysis, meaning that one looks into the individual components of a robot or the processes that it is supposed to fulfill, then considers failure modes which might take place, analyzes the probability at which those events take place as well as their severity, and then defines safeguards in order to prevent those accidents from taking place. Those measures are colloquially called risk reduction measures, and they usually relate to safety-rated monitored stops, hand guiding operations, speed separation monitoring, as well as power and force limiting. And one of the last steps that is very important and should never be forgotten is that those things should then be trained and educated to the personnel which are going to be in contact with the industrial manipulator. So far, we haven't talked about ISO 15066, robots and robotics devices, collaborative robots. As aforementioned, a collaborative robot in terms of the ISO standard is defined as one that does fulfill a collaborative operation, meaning that the operator and the robot share a collaborative workspace, which is very ambiguous, and it means essentially that there is a concurrent task between the industrial manipulator and the industrial robot. That is why I would like to supplement this definition by the ISO here with an additional definition coming from the International Federation of Robotics, which defines 5 levels of different types of collaborations, and also including a fixed level, which is not part of the official definition, but can be found being used by some of the robotics original equipment manufacturers, as well as some researchers. So the lowest level of collaboration is the cell level, as you can see in figure 22. Cells are characterized by physical barriers which exist between the robot and the human cannot enter into the robot's working space. In this case, you see a human in the working space of the industrial manipulators being depicted in figure 22, But that also means that according to the European Machine Directive, that all the machines which are part of this robot cell are shut down. So, characteristically for a cell are fences. Fences are used to prevent entry to the robot's working space. The fence is also a preventive action against losing parts out of the gripper. Barriers could be a different type of protection, preventing the worker from entering the cell through the load or unload area. In special cases like laser cutting, arc welding and water jet applications, the system is completely encapsulated. Another characteristic aspects are interlock barrier gates. This is a physical barrier around a robot's work envelope that incorporates gates equipped with interlocks. These interlocks are designed so that all automatic operations by the robot and associated machinery will stop when any gate is opened. Restarting the operation requires closing the gate and reactivating a control switch located outside the barrier. A typical practical barrier is an interlock fence designed so that access through, over, under or around the fence is not possible when the gate is closed. So, the next higher level is coexistence. Coexistence defines that there are no physical barriers to separate the working spaces, but line fences or presence sensing devices lead to a program stop. Characteristic for robotic cells that use coexistence are mechanical limits, as well as position switches. Mechanical limits are used to reduce the working area for the robot. Historically, the fences around the robot system have been outside the robot's maximum workspace. Due to the complex cell layout design, it wasn't possible to mechanically reduce the working area of the manipulator in most cases. In particular, the bending backwards kinematics are extremely difficult to limit to the working range of axes 2 and 3 because the robot's working range is needed for the front area, but it should be limited in the area behind it. Then there are position switches. A position switch is used to indicate where the robot is working right now. In traditional robots, there are position switches for axes 1, 2 and 3 to indicate whether the robot is entering the area or not. This is used for machine protection or for personal safety if the robot and the worker have the same workspace as in the coexistence cell layout. The next higher level of collaboration is sequential collaboration. In the case of sequential collaboration, both the robot and worker are active in the same workspace, but their close proximity movements are sequential. That is to say that only the robot or only the worker moves. Characteristic for those cell layouts are presence sensing devices as well as audible and visible warning systems. Audible and visible warning systems are not acceptable for safeguarding methods, but they may be used to enhance the effectiveness of positive safeguards, such as the presence sensing devices. The presence sensing detectors that are most commonly used in robotic safety are pressure mats and light curtains. Floor mats, pressure sensitive mats, light curtains similar to arrays of photocells, and laser scanners can be used to detect a person stepping into a hazardous area near a robot. Effective presence sensing devices stop all motion in the robot if any part of the worker's body enters the protected zone. They are also designed to be fail-safe so that the occurrence of a failure within the device will leave it unaffected or convert it into a mode in which its failed state would not result in an accident. The next higher states are cooperation, meaning that both the worker and the robot are active at the same workspace at the same time, and both the robot and the worker move. Then there is responsive collaboration, in which the robot responds in real time to the movement of the worker, and as said, there is autonomous collaboration, in which case the robot is also able to move its base coordinate system. And for all the categories 4 to 6, the additional safeguards that one will find in addition to the already named presence sensing devices are force torque sensors that identify the force that is being exerted by the robot onto its environment, or torque sensors which identify how much torque is being needed in the joints, and if there is a deviation between the nominal required amount of torque in order to fulfill a movement, identify the contribution that comes from the human, as well as close proximity sensors such as contact sensors in order to deactivate the robots.